All right, so to give ourselves a little bit of a running start, this is that same example we ended on last time. We had our step 1 where we found the associated homogeneous differential equation. I didn't actually write it out. I think we did write it out last time, but I just put the characteristic equation in here when I was rewriting this right before class. We solved for the roots of the characteristic equation. We then saw that those two roots were different or distinct and popped the roots into the appropriate format for these individual solutions right here. We then went ahead, and not everybody does this in step 1, but we then went ahead and found the actual homogeneous solution. Some people actually wait on putting it together till the 3rd step, but that's personal preference. Then we went ahead and said we found the general format for our guess for a particular solution. Namely, it matched exactly the same format that we had right up here for our non-homogeneous part. And let me go ahead and label this. So this guy right here, this is our f of x, the non-homogeneous part of the differential equation. Notice it had 2 things added together, the polynomial part. That's the part that's the 6x squared plus 10x plus 2. The 10x plus 2 actually doesn't matter in terms of the general format for your particular solution's guess, because as soon as you have the degree 2 polynomial, you're going to have all 3 of these terms of the degree 2 term, the degree 1 term, and the degree 0 term. Although that's probably an awkward way of saying it. Okay. Then we had the second part of the non-homogeneous part of your differential equation. Here, since it's exponential, we just totally said, hey, it may not have a coefficient of 12, but we know it's just going to be some constant coefficient. Okay. So there's our running start in terms of what we've done previously. Now, going forward. So going forward here, notice your differential equation up at the top, so the part right after where it says solve. We're going to want to plug our particular solution in there. And I'm assuming that most of you, hopefully all of you, have started working on the web work for this section already, so you know what's about to happen. We're going to go ahead and find the first derivative, and then we're going to find the second derivative of the particular solution. Why? Because we're about to plug them into the actual differential equation. So if we take the first derivative, we'll get 2ax plus b. And the term with the e to the x doesn't change, so still d e to the x. And then for the second derivative, we'll get 2a plus d e to the x. And at this point, we're just going to plug everything into our originally given differential equation. So we'll have, and I'll go ahead and signpost what we're doing. So second derivative plus 5 times first derivative plus 6 times the actual format of our particular solution. So we'll have ax squared plus bx plus c plus d e to the x plus 5 times the first derivative. Our first derivative was 2ax plus b plus d e to the x. And then what we had 5 times the original guess, not 5, 6 times the original guess. That's 6 times ax squared plus bx plus c plus d e to the x. And then you combine like terms. So if we go ahead and combine like terms here, we're going to end up with following. Except I think I totally messed something up. Anybody see what I messed up? Yep, you totally nailed it. I just did something that I have a tendency to do all the time, and it's completely something you should definitely not do. I didn't plug in the second derivative for the second derivative. I just read straight down the first equation, the second equation, and then I paid attention to the last one and got the original. So this guy should not have been the original particular solution. It should have been the second derivative. So I'm going to go back and cross off the part that's different, and that should be 2a. Happens to everybody. So you pay attention to what you plug in where. So now that that's fixed, you group like terms. So I'm going to start off with the second derivative. So if we, not second derivative, x squared, excuse me. So if we look for all the terms with x squared, turns out there's only one of them, and it's that very last thing we plugged in. So right here are ax squared, or really, don't forget about the 6ax squared. Next, a look at the term with an x. So if we look at the term with an x, and let me see if I can get a different color. If we look at the term with an x, we have one of them here from the original guess. We've got one of them here from the first derivative, and those are the only two terms with an x in them. So I'll just go ahead and pull those terms down. Don't forget to multiply by the 5 and the 6. So we'll have 5 times 2a. That would be 10ax. I already pulled the x out, so I'm just going to write 10a. And for the other one that came from the bx term, that one, don't forget about the c. So this, not c, the 6. This one would be 6b. And I already pulled the x out. So last polynomial term would be all the terms that have constants or that are only constants. So for this one, it looks like there should be 3 of them. We've got just the c from the original guess. We've got just the b from the first derivative of the guess. And then we've got that corrected term from our second derivative. So put all those guys together. So we'll have 2a. B really has a 5 being multiplied by it, so 5b. And the c really has a 6 multiplied by it, so it's really 6c. And then the last expression would be dealing with all of our e to the x terms. So we have, what do we have here? We've got a d e to the x, so one of them. Then we have 5 times d e to the x, so an additional 5 of them. And then we have 6 d e to the x, so an additional 6 of them. So this is going to be, notice there's a d e to the x on all of them. But if you add them together, what should be the coefficient in front of that d? And I'll let you guys tell me that coefficient. So 1 plus 5 plus 6, so that'll give us 12. Now I went ahead and just jumped to that answer, or really had you guys jump to that answer, mainly because I'm starting to get tight on space here. If you're doing this on your own, don't try to skimp on this. Definitely get a blank piece of paper and just write as much as you need to write. So for example, I believe there's a paper or handwritten homework set attached to this. Don't feel constrained by that actual PDF or printed page that you can print off. If you want to just write it on your own piece of paper so you can have plenty of space, definitely do that. These problems can get long. Now, what's this thing supposed to equal? Well, this whole thing is supposed to equal, and I'm going to highlight this as it being supposed to equal by the slightly different purpley color, and let's see if that'll actually work. All of that is supposed to equal our 6x squared plus 10x plus 2 plus 12 e to the x. And notice this here, that is totally our f of x from the original differential equation right there. Now, what does all of that mean for us? That means we're about to set up some systems of equations. Okay. So this is going to equate to match your like coefficients or your like terms. So for example, your x squared and your x squared terms have to match. So this means our 6a has to equal 6. In other words, we know that a equals what? A would have to equal 1. We also would then get, when you look at the x term, that 10a plus 6b is supposed to equal 10. Now, what does that tell you that b has to equal? Because remember, we already know a equals 1. Have to equal 0. And if we look at the constant terms, so this would tell you that 2a plus 5b plus 6c, and remember we already have a and c, is supposed to equal 2. So anybody have a guess on what c would have to equal? And it doesn't, what c would have to equal there? Yeah, it would actually still be 0 in this case. And the only guy that we haven't done yet, and I'm going to go ahead and just circle it because I'm running out of space here at the end, are these two guys. Actually, I may be able to fit it in at the very bottom there. So this tells you that, oh, awesome, you can sort of see it. 12d e to the x equals 12 e to the x. So this means d has to equal what? Oh, you guys are already telling me. Awesome. So d has to equal 1. So at this point, I've completely ran out of space on this slide. So what I'm going to do is I'm going to take the key pieces of information that we care about, which is our homogeneous solution at the end of step 1, and then those 4 numbers, the A, B, C, and D, and we'll go ahead and plug it into our guess for our particular solution. So here's our guess for our particular solution. Notice when you plug in B and C both equaling 0, those middle two terms are going to completely disappear. So I'm going to let you guys tell me what should the particular solution be as I start writing the stuff that we need on the next slide. So we'll get x squared plus e to the x, which means if you want your general solution, let me go back. Didn't mean to go back that far. Just a second. If you want your general solution for your non-homogeneous differential equation, in other words, our step 3, find y, what should we do with the 2 answers from step 1 and 2? Yep, just add them together. So our answer for y would simply be c1 e to the negative x plus c2 e to the negative 3x plus x squared plus e to the x. And here is the key. I cannot stress this enough. This is the key thing. Your particular solution must not have any constants left in it after you've gone through step 2. Okay? So don't add the 2 components together. Don't add the particular solution and the homogeneous solution together until after you've gone ahead and solved for all of those coefficients in your particular solution. That's got to be probably the most critical thing to take away from this method. Okay, probably not. The most critical thing is how to do the method, but that is a very, very key component. Now, I'm going to add on something to this question. Okay, here's the add-on to the question. Suppose you were asked to do the following. Solve, and I'm going to just rewrite our differential equation, so let me look back for what it was. It was second derivative plus 5 times the first derivative plus 6 times the original, and then a bunch of stuff. This was 6x squared plus 10x plus 2 plus 12 e to the x, where we have something extra. Suppose you are told that when x equals 0, y is supposed to equal 2, and when x equals 0, the derivative of y is supposed to equal 0. What changes about this question if you now have that new information? Don't overthink it. What's the only difference between that orange writing that we just put in and the original statement? It totally has to do with your C1, C2 constants, right? The only new thing here is you're going to actually go and find out those values of the solution, and the actual solution here is a particular solution. Now, it's not any old particular solution. Method of undetermined coefficients gives you the simplest particular solution that you have. What we're going to find out is a particular solution that meets those 2 initial conditions. So this here is where we do the same thing that we would have done back with our first order differential equations. You just plug in and solve for C1 and C2. So let's do it. So I would recommend always dealing with your initial condition that is not the derivative one first, just because it's easier. So here, if we go ahead and take our solution, I was back up here under step 3. This is like a step 4, if you will. So step 4. We'll go ahead and we'll plug in x's equals 0 everywhere and y's equal 2 everywhere. Well, if y is equals 2, we'll have 2 equals c1 times e to the 0 plus c2 e to the 0 plus 0 squared plus e to the 0. So this guy here is where we used y of 0 equals 2, and in the future I'll try to title that better. Now that, of course, is a mess. You should totally clean it up. And if you clean it up, you'll get c1 plus c2 on that right-hand side. 0 squared disappears, and what does the e to the 0 turn into? So what I would probably do if I was doing this not in front of all of you guys is I'd probably go ahead and just subtract the 1 from both sides in that same last step. But either way, whether you do it in 1 step or 2 steps or 3 steps, what you want to do is you want to get your C1 and C2s all by themselves. So if you have an extra plus some constant, move it to the other side. If you want to, you can actually totally go ahead and solve for either C1 or C2 right now. If you did that, you would have C1 equals something something C2. Okay. Now, this is one thing that we're going to need in the future. So write that down somewhere because we're going to need it here in just a second. But I got to go to the next slide because I used up all my space. Okay. So what we're going to need is we're going to need our same general solution of the differential equation. We're going to need what we just found using the first initial condition, and now we're also going to need our second initial condition. So while I'm writing down that step that we're going to need on the next step, think about how we would use our second initial condition. So what are we going to need to do in order to deal with this second initial condition? Because we can't just plug it in right now. We can't just plug in zeros everywhere that we want to. Yep. First, we've got to take the derivative. So if we take the derivative of our general solution that we currently have, this one right here written at the top, what is that derivative? Well, the first term turns into negative c1 times e to the negative x. Second term turns into negative c2 e to the negative 3x. And I'll let you guys tell me the last 2 terms. What should the, or you've already got it, awesome. So the next term would turn into 2x, and the last term would turn into e to the x. Now, once you have your derivative, what are we going to use or do with that derivative? Don't overthink it. Yep, this is the point where you want to plug in stuff. So everywhere there's an x, we're going to plug in 0. So you'll get negative 2c1, and then this e is going to be e to the 0, but e to the 0 is really 1. Second term, we'll get minus 3c2, and again, we'll get e to the 0, and that guy is really 1. We'll plug in 0 for 2x, but what happens when you plug in 0 for 2x? Hopefully you are all thinking it completely disappears because it's really 0, so I'm not going to write anything down. And last term is e to the x, so that's really e to the 0. And e to the 0 is the same thing as, hopefully you are all thinking 1. Now, let's go back to the thing that I skipped. Here in our formula, we had y prime, or the derivative of y. What should I plug in as a number value on the last line we have written so far? So 0, and that 0 came from the initial condition right there. Notice what we have right here. We can totally rewrite this guy as 2c1 plus 3c2 equals 1. And notice we already have a second equation up there that deals with c1 and c2. So this is the point where you use a little algebra. And you flash back in your head to something like high school algebra or college algebra, or if you took linear algebra, where you go and you solve for C1 and C2. Now, would you guys like me just to tell you what C1 and C2 are, or do you want me to go through the 2 steps to find it? Or find them, since there's 2 of them. If you would like me to find C1 and C2 explicitly, give me a check next to your name if you can. I have 2 votes of any type. All right, I've got not lots of votes, but there are more of them for me to go through the steps. So to remind ourselves of the algebra, here's what you do. You can do it in multiple ways. This way, it has a tendency to work a lot of the times. We can't solve for 2 unknowns in one equation, so we're going to use the second equation to get rid of one of the unknowns. So I'm going to multiply this guy by, I don't know, how about -2? Okay. Now, if we multiply by -2, that means we're going to get coefficients on both the C1 and the C2. What would be the advantage of multiplying by -2 here? Any guesses why I chose that -2? Yep, this is totally so that we could eliminate one of the 2 variables, in this case the C1, but what would have been the other strategic number that we could have chosen to multiply that equation by? 3 or -3. Some people prefer to multiply by the negative like what I did. Some people prefer to multiply by the positive and then just think of subtracting the 2 equations. What we're going to do here is we're going to add the 2 equations. And when we add the 2 equations, the C1 disappears. 3C2 minus 2C2 is going to be a single C2, and that now gives you the answer for what C2 would have to be. Then go back to either of the 2 equations that you started with. So that would be this one, or the other circled one up in the corner. Again, it doesn't matter which one you use. I'm going to use the one up in the corner. I'm going to go ahead and solve it for C1. So according to that equation up in the corner, C1 equals 1 minus C2. So then you go ahead and plug it in. And when you do that arithmetic, you should be getting 1 minus -1, which is 2. Be careful it's not 0. Super easy mistake to make. Now, once you have your C1 and your C2, what are we going to do with them? What should we do with those 2 values? C2 being -1 and C1 being +2. So we'll plug them back into our format for our solution, specifically our general solution back up here at the very top. So y here equals C1. C1 was 2, so 2e to the -2x minus e raised to the -3. You just plugged in the -1. And then the rest of the bit, the original particular solution we got from method of undetermined coefficients, that part doesn't change. So this now would be the solution to your initial value problem. Okay? So that's really the only piece that we hadn't talked about too much previously, was what happens if you have initial conditions. It's no change from the rest of the semester. Get your general solution for your differential equation, and then the very, I can't repeat this enough, very last step is where you go ahead and plug in whatever values you have for your initial conditions. Question about this problem? Kind of okay so far. And I think you have several of your homework questions that deal with initial conditions. So that would be how to finish those guys off too. All right, I am not seeing any questions come in from you guys. So for the rest of today, the plan is to start talking about our next method of solving the non-homogeneous differential equations. Okay? And for this one, because of tests and classes, etc., I didn't actually get a chance to type anything up for you guys, so I'm going to move to a different program that I can write in a little easier. All right, so let's get, All right, you should just have one screen being shared with you now. All right, so first of all is what section in your textbook this is coming from. So this here is coming from section, oh no, let us not do that. Just a second, let us get a slightly more sane drawing implement. I think that one is probably going to be better. All right, so we have got section 4.6. The method we are going to be building up to by probably the end of today or beginning of next time is going to be what's called variation of parameters. Variation of parameters. Now this method of variation of parameters you only apply to non-homogeneous differential equations. So that means you have to have a term that does not have your dependent variable in it. It will work anytime your method of undetermined coefficients works. So if you never want to use your method of undetermined coefficients again, other than for a test or paper homework question where I will ask you to use that method, that is totally okay. This method will work in far more situations than what we're going to do in our class. So I'm going to show you specifically what you would do in a second order non-homogeneous differential equation. Now, in order to use the formula, because there's no guesswork involved in variation of parameters, I'm literally just going to give you a formula of this is what your particular solution looks like. Okay? In order to get that formula, we have to compute something called the Wronskian. So the first part, possibly most of the rest of our time together today is going to just be talking about the Wronskian and what it is. So if you have any questions, make sure you let me know because you're not going to be able to get through variation of parameters if you can't get through the Wronskian. So first thing, let's go ahead and look at what the Wronskian is. So definition here, that is a really ugly green. Oh well, we started with it, we're going to finish with it. And now we'll pretend we didn't. So I'm going to go with a W. Technically speaking, you can also, W is for Wronskian, you can also have parentheses after it. The Wronskian is going to be of functions. So what people will often do is they'll list out what functions they're plugging into the Wronskian. I'm going to give you the general pattern right now, which would be for an arbitrary number of functions, so n functions. When you actually compute this for real, you'll know how many functions you have. You'll have 2 or more. So all of the examples we're going to look at today are going to be if you have 2 or 3 functions. So this is the formula. First thing that you do is you just list out all of your functions that you care about in a row. And since I said n functions, and I don't know what the number n is yet, I just put dot, dot, dot to indicate you keep going until you put your last function there. Now, that's the first row. Second row is you take the derivative of all of those functions and put the derivative of the function directly under its function. So first you write the derivative of f1, then you write the derivative of f2, derivative of f3, and you keep going until you dealt with all of your functions. Any guesses what's going to happen in the third row or next row? Yep, next row down is going to be second derivatives. That's how you build this thing. Keep taking derivatives from each consecutive row. So next guy will be second derivative of each of these functions. Make sure your subscripts here match, and make sure you actually put the second derivative symbol, like I almost forgot. And then you keep on going. Now, how do you know when to stop? You have to have the same number of rows as columns. So each of our columns is based off of one of our functions. So in this case, we have n functions, so n columns, which means we need n rows. So we're going to stop when we get to not the nth derivative, but the nth minus first derivative. Why the nth minus first? Because the second row deals with the first derivative. So the up here is one less than what you might expect. So for second function, still the same, n minus 1 derivative. Third function, still that n minus 1 derivative. Keep going until you get to your last function. And remember those parentheses around that number and what looks like the exponent really means derivative when you have a function. All right, now here's the extra symbols. We have just made a square n column, n row block of functions. Okay, what look like absolute values around the first and last part, or the left and the right side of that block of functions, is actually telling you two things. First thing it's telling you is you just built a matrix. If you don't know what a matrix is, don't worry about it. It is literally just in a figure format, something that looks like a rectangle, or in our case a square, and has entries in each one of the rows and columns. Okay? In other words, it literally looks like a either square or rectangular shape of entries. Okay? Now, the absolute value symbols, or the things that look like absolute value symbols, are actually what's known as the determinant. If you have ever dealt with a determinant before, such as taking linear algebra or Calc 3, it's the same thing as what you would have done in those classes. If you have not taken either of those two classes, don't worry about it. I'm about to tell you what the formula is. Okay? Now, since neither Calc 3 nor linear algebra being the more important one here, are prereqs for our course, we're not going to be dealing with Wronskians of an arbitrary number of functions. We are only going to be dealing with Wronskians if you have 2 or 3 functions, because those are the only two situations where I'm going to tell you what the formula equals. I'm not going to give you the general formula for the determinant, only the specialized cases when you have a 2x2 or a 3x3 matrix. Now, before we jump into how to compute this Wronskian, in other words, how to compute that block of functions with the symbols that look like absolute values, here's how you use it. So let me go ahead and signpost what we're doing here. So, uses. Or maybe I should write interpretation. Interpretation. Okay. So the Wronskian tells you a lot of things. First thing is, if the Wronskian always equals 0, in other words, you compute this thing, which I haven't told you how to do yet, and you get back a big fat 0, what that tells you is your original functions, so the F1, F2, however many original functions that you use to build your Wronskian, these guys are linearly independent. I'm abbreviating here simply because I'm about to run out of space. Okay. Now, remember what linearly independent is. We talked about that when we were building our small little functions for both the homogeneous solutions, as well as when we were dealing with our particular solution method, undetermined coefficients. Linearly independent meant that there was no way to write one of the functions in terms of the other function. Wronskian here now is, instead of visibly looking at it and trying to think if there's any way to do that, this is now going to give you a formula to say, hey, don't overtax your brain, just plug it in the formula. If you get back at 0, then these guys are, and I messed up, just a second, then these guys are linearly dependent. Sorry about that. Because we're actually going to need the Wronskian to equal not 0, because it will be in the bottom of a fraction when we get our formula for variation of parameters. So, if our Wronskian is not 0, then it turns out that these functions are linearly independent. Sorry about that, guys. Make sure you correct it in your notes if you're writing things down. These guys are linearly independent. So this is the one that we're going to want. Now, there is a case where, and we're going to see this, where you compute your Wronskian and it's not just a number answer, it's a formula. And sometimes when you get back a formula or a function, like e to the x is never 0, so no worries. But maybe you get something like x squared. Well, x squared is sometimes 0. It turns out wherever the Wronskian is not 0, that's where your solutions are going to exist. If the Wronskian does equal 0, it would be like back in an algebra class and you graphed something and you had a hole in the graph. that's sort of what would happen here if the Wronskian equals 0 at one x value, or one independent value. And it's a little different, but it's close enough that that gives you the right idea. And we'll see some examples of that in a little bit. All right, if we look at, where's a decent color for this? How about this one? So uses. And we actually already said these, but let me go ahead and write them down for us. The main uses are, well, twofold. The first one is, this is take however many solutions you have, and this you'll be able to figure out if they are linearly independent. The other one, where it's uses, is it'll be used in the formula or our variation of parameters. All right, so that's all the background information that we need. Now we're ready to go ahead and actually see what's happening. So specifically here, if you have two functions, so this is when n would equal 2, your Wronskian, and if you write it when you list out what your functions are, maybe you list out your functions like this, and I'll go ahead and just use f and g without subscripts, just so it's easier to write. What would you do? Well, the first thing you would do is you would list out whatever two functions you have, and what did we say we wrote below those two functions? So below those two functions, in the first position, I'm going to write first derivative of f, and in the second position, I'll write the first derivative of g. Okay? So at this point in time, what have we done? We've literally just mimicked the definition up here, where we've built ourselves, we only have two functions, so we only go out to two columns, and we're only going to go down then to two rows. We know we're going to stop as soon as we have that first derivative row, because two rows, two columns. You got to be a square in terms of formatting. Now, in terms of actually getting this answer, well, we haven't said that yet. So here's how you do it in 2 by 2. You are going to multiply down the diagonal of the matrix. So you'll multiply f times g prime. Then you're going to subtract, and you'll multiply up what I'm going to call the off diagonal here. So this one would be our f prime times g. I didn't totally mean to have that a different color, although it worked out because it kind of matched that blue highlighting. And that's it. Notice it kind of looks like the product rule, but there's a subtraction sign in there. And that is literally it in terms of how you deal with a 2 by 2 determinant. And like I said previously, if you've done linear algebra or Calc 3 or something like that, you've probably seen this one before. It is the exact same deal. So let us look at some examples. And I think I've got 2 prepped up for us, and then we'll jump to what happens if you have 3 functions. So suppose you have the 2 functions cosine and sine. Okay? And suppose you want to know, are these guys, so here's the actual question, are they linearly independent or not? In other words, are they linearly independent or are they linearly dependent? Now, we've actually looked at those guys before when we looked at the definition of what linearly independent or dependent functions were. Anybody remember what conclusion we came to of whether those functions were independent or dependent? Sorry about that, guys. Thoughts? Remember, linearly independent means you cannot write one of them as a multiple of the other. Can you write one of those functions as a multiple of the other? So that now tells us, yes, these two guys are supposed to be linearly independent. We said before, we have no idea what constant, what real number you'd use to multiply, say, cosine by to get sine, and in fact, you can't. The only thing you can do is shift them, and that doesn't deal with multiplying by a constant, excuse me. Now, what would that mean in terms of calculating the Wronskian? So if we calculate the Wronskian of this guy, we should get what as an answer? Would we, yeah, not 0. The best you can say right now is not 0. Now, do we know what the actual number is? Nope. But can we find it? Yep, and we're going to do that here in just a second. And when I say just a second, as soon as I move it up so I can actually write. All right, so if we wanted to find the Wronskian of this guy, we'd say, hey, W equals, and then we want to figure out which function we want to write first. So do you guys want me to write cosine or sine first? Hint, it doesn't matter in terms of independent or dependent, but it will matter later on. So who would you guys like to see first, sine or cosine? Cosine? All right. So if we go ahead and write cosine first, I'll write sine second. This then tells us that when we form our Wronskian, make sure you write the cosine first and the sine second. And we'll actually see what happens if you reverse them. Now, second line or second row. What should I write for the second row? Under the cosine, I should have what? Negative sine. And anybody got what I should write under the sine? Cosine. So now we're ready to actually compute what the Wronskian would be. I'm going to go ahead and color code it for us again. First thing that you look is you multiply down the diagonal. If you multiply down the diagonal, we're going to multiply the cosine times the cosine, or let's be lazy and just write cosine squared. Then we're going to subtract, and then we're going to multiply up the diagonal. Now when you multiply up the diagonal, you've got sine times negative sine, which is exactly the same as, well, let's be lazy and write the condensed version, negative sine squared. Which means, what does this guy actually equal? Hopefully you are all thinking cosine squared plus sine squared, but who is that really? Ooh, and you guys got it already. That would equal 1. So, did we get an answer that was not 0? Hopefully you're all thinking that's not 0. Let me put the slash through there. Now, what conclusion would that mean? The conclusion then that we would say here is, therefore, cosine and sine are linearly independent functions. And I know I abbreviated linearly and independent and functions, but if you wrote it all out with their full words, that would be the very, very proper way of saying it. Questions? Make sense? Kind of feeling okay-ish. All right, I'm not seeing too many people fuss, or really anybody fuss. So let us look at, I told you what things can happen if you flip-flop the functions. So if that's an A, that was the main thing. What happens if you did the exact same thing, except you flip-flop the order of the sine and the cosine? Anybody have a guess on what would change? Don't overthink it. Ooh, not what I was looking for, but yes. So what would change here is the columns would rearrange. So you would get sine first, then cosine, and when you put the derivatives on the bottom, you'll get cosine below sine. Notice that matched the same as before. And below the cosine, you'll get a negative sign. So our columns just flip-flopped. When you compute this, you'll get your sine times your negative sign, so negative sine squared. You'll subtract the off diagonal, so you'll subtract your cosine times your cosine, or your negative cosine, and notice what happens. You'll then get, well, you can factor out a negative sign, and you'll get negative cosine squared plus cosine. I said it wrong, but wrote it right. Negative sine squared plus cosine squared, or there's that negative 1. Okay? This actually is true anytime you jumble up or rearrange the order of the functions. If you rearrange the order of columns in a matrix, your determinant may flip signs. So for example, in a 2 by 2 matrix, it'll definitely flip signs. In a 3 by 3 matrix, depending how you jumble the columns, it'll either get changed by a negative sign or get changed by a negative sign twice, which means it's really the same. Now, good news, we still got a negative 1 there. Did our conclusion change? Are sine and cosine still linearly independent? Yeah, so that's the great news about the Wronskian. When we're just comparing it to 0, it doesn't matter if our answer has its sign flipped to positive or negative, depending on the order that you put your functions, you're still going to get the same conclusion. Now, here's where it does matter. In our method of variation of parameters that it looks like we're going to really focus on next time, that answer from the Wronskian is going to be one of the components in the actual equation. Well, if your component in the equation, that negative changing, that'll matter, okay? And that's one of the reasons I wanted to go ahead and show you this way of writing the Wronskian, because it's going to show you the order that you're going to need when we start plugging things in to calculate a Wronskian in the future. All right, so that was one example. Let us look at another example. And this next example that I'm going to pull is, suppose we have e to the x and x times e to the x. And again, the question is, are they linearly independent or linearly dependent? So here, again, these are two guys that we have seen in the past. And we've said in the past that they have to be linearly independent. In fact, our trick for making two functions that were the same, making one of them linearly independent, was multiplying by an x, or the independent variable. Okay? So what should we get? We should definitely get a Wronskian not equaling 0 in this case as well. Okay? So let us check out the Wronskian. And I'll just go ahead and write them in order, just because I'm lazy. The first row is just the e to the x and the x e to the x out of the easy part. Second row, derivative of e to the x, that is also e to the x. Now, the only thing about this one that's hard is checking out the derivative of x e to the x. Does anybody have it? Yep. So it's totally going to be product rule, so I'll talk us through it. So product rule says derivative of the first, which is 1. So 1 times e to the x. So that means I'm going to write it in the reverse of the way that you wrote it. Ooh, yes, you could also do factored form. And then if you have the original first times the derivative of the second, you'll have x times e to the x. And you can totally factor this guy if you want or not. It doesn't matter. Okay? Some people always prefer factored form. Some people don't. Some people prefer to write it the two terms in opposite order. Personal preference, as long as you get the derivative, how you write it down there doesn't matter. So let's go ahead and compute this guy. The first thing we do is we're going to go ahead and multiply it down the diagonal. This would say that we have e to the x times e to the x plus x e to the x. And then we're going to subtract. And the thing that we subtract is we'll multiply by the off diagonal, or the going up way. So in this case, when we have e to the x times x e to the x, well, it's all just one term, so you've got the x. Whoa, don't do that. Oh, no. You have the x, and then you have e raised to the, anybody have a guess what that exponent's going to be? What should be the x, the exponent over here on that e? So you'll have e to the x times e to the x, so the exponents add, so you'll get 2x. Now that's important because we're about to multiply through on that first term. So if we multiply through on the first term, you'll have e to the x times e to the x, so that's e to the 2x. And then you'll have e times x, e to the x. And notice that's going to be a single x and then e to the x squared, or e to the 2x. And then minus the thing that we already computed, so x e to the 2x. Obviously, things cancel. So what should be the final answer? Yep. So final answer right here will totally just be our e to the 2x. Now, here's where the analysis comes into play. We've got the expression for our Wronskian. It's a function this time. It's not just a number 1 or a negative 1 like in the last example. Does this function equal 0? It does not. And in fact, it doesn't matter what x you plug in. This guy is never going to equal 0. But even if it equals 0 and 1 or 2 x's, that's actually still okay. But here, what does this tell us? If your Wronskian never equals 0, this tells you that e to the x and x e to the x must be what? Are they linearly independent or linearly dependent? They would be linearly independent. And that's literally all you would do for the 2 by 2 case. By far, we're going to see where we use 2 functions the most. So this here, if you understand those 2 examples, that's going to be the main thing that we're going to be dealing with in our course. If our course had a prereq of linear algebra, we'd be looking at Wronskians of all sorts of sizes, however many functions we want. But because linear algebra is not a prereq, we're really going to stick mostly to when you only have 2 or 3 functions being plugged in. Well, only 2 or 3 functions plugged in, mostly just 2. But let's go ahead and finish off what I said I'd tell you about, which is computing Wronskian for 3 functions as well. So let's do that next. Any questions before we move on? All right. So if you have 3 functions, so this is n equals 3, goes as follows. Actually, for this one, let me go ahead and show it to you inside of an example, just because it'll probably be easier that way. So suppose you are looking at, and I'll label these guys. Some function, maybe the first function is 1. Second function, let's make this guy x. A third function, make this guy x squared. So here's the first thing that we know for sure. We know for sure that our Wronskian, I'm going to go ahead and write it where we can write the functions inside of these parentheses, is going to be formed where you write all the functions in a row. So we've got the 1, we've got the x, we've got the x squared. Now, the next row down is just going to be all the derivatives. So the derivative of 1 is 0, the derivative of x is 1, and the derivative of x squared is, well, 2x. Now, last row. The last row, we'll take derivatives again. So we'll have, I'll do the easy 2, 0 and 0. And what is the last derivative there in that third row need to be? Yep. Totally a reason I picked these guys. 1, you see them quite a bit when you start jumping into the differential equations. And 2, it's super easy to calculate. All right. So here's now where all the fun part happens. Okay. So first thing you want to do, and if I had a pencil, that I do not have here. What I would do is I'd actually ink up this part, the Wronskian format formula right here. And then in pencil, I'd write what I'm about to write over here because it's going to be scratch work. I don't have that for us today, so I'm just going to use a different color. So what you do is you take your first two columns, and you're just going to copy them down. Whoops. Don't overthink it. You literally just copy it down. Okay? Now, we're going to actually calculate what we're going to do next down here. And here's what we're going to do. First thing is we're going to do the same thing that we did in the 2 by 2 case. We're going to multiply down the diagonal. Except notice, by putting those extra two columns, we now have two other quote-unquote diagonals. They're not actually called diagonals of the matrix, but they are essentially parallel to diagonals of the matrix. So there and there as well. Now down each of these diagonal stripes, if you will, we want to multiply all of the numbers that are inside of those diagonal stripes together. So we've got 1 times 1 times 2. 1 times 1 times 2. We'll then do the same thing on the next diagonal stripe. This one is x times 2x times 0. And then we'll do the same thing on the last diagonal stripe. This is x squared times 0 times 0. Okay? We're going to add all of those components together. But of course, we can actually figure out what those guys are right now. 1 times 1 times 2 is, of course, 2. And what do the next two terms turn into be? Both of the next ones will be 0. So what I'll often do when I'm calculating these guys, I'll actually go ahead and write the zeros in there just to remind myself, hey, don't forget, yeah, I really did deal with all three of those stripes. Now we're going to replicate the same process that we did in the 2 by 2 matrix where we multiplied up the off diagonal. So we'll start with multiplying up the off diagonal. And please note we're having to do this because notice there are 3 entries of our matrix right here that we haven't used yet. So starting by multiplying up the off diagonal, and then just like our same situation that we did earlier, where we went and had 2 more sort of parallel looking stripes, we're going to do that here as well. Okay? Now, what are we going to do with those 3 sort of diagonal looking stripes of information? Well, the exact same thing we did with these stripes that are highlighted in yellow. Or in each of those diagonally oriented stripes, we're going to multiply all 3 terms together, and we're going to do it for each of the 3 stripes. This first stripe right here is 0 times 1 times x squared. So 0 times 1 times x squared. Next one is 0 times 2x times 1. And of course, when you're doing it yourself, if you can multiply all those guys together in your head, go for it. And then the last stripe is 2 times 0 times x. I'm on purpose putting out what we're doing so if you come back to this later, you'll know what happened because I didn't write out a general formula. It just gets complicated with that however many letters you use to go into the 3 by 3 matrix. So now let's go ahead and collapse this down. Each of those 3 terms are all going to equal what? Did anybody pick up what each of those 3 terms were going to equal? Yep, so each of those 3 terms does have a factor of 0 in it, so every single one of those guys would actually turn into zeros. This is an extraordinarily nice determinant to calculate. Why? Because notice in that last line there, we literally have one non-zero number, which means our determinant here is, once we simplify, a 2. Now, just as a heads up, this is what's known as a, I shouldn't say that, this is a shortcut formula. Every single of one of those 9 entries in the formula right here between the lines that look like absolute value lines were used exactly twice. The ones that don't look like they were used twice, for example, this 0 here, it was actually the copy of the 0 right over here that was used twice. This guy down here, the 0, it was used once here, and then its copy was also used one more time. So each one of these guys were actually used exactly twice in our formula. There is another formula, which is the official rule for calculating a determinant, and it starts working on 3x3 matrices or 3x3 determinants. If you know it already, that's totally fine. Feel free to use it. I'm not going to tell it to you guys in this class simply because I don't want to give you tons and tons of extra information. Okay? But as soon as you get into a 4x4 matrix situation, you have to use that real formula, not this shortcut that I just shared with you. Okay? But this is a shortcut that people like to use both in Calc 3 when you're in 3 dimensions and also in differential equations just because it's, well, it's a shortcut. Okay? So that would be how to use that guy. Let us look at one more example in the 3-function case, and then that'll be it in terms of Wronskian. So let's finish off the current example. Suppose somebody asked you, hey, are those 3 functions 1x and x squared? Do we think they're linearly independent? What would you say to them? Do you guys think those 3 functions are linearly independent or not? So since our Wronskian equaled 2 and not 0, what we get, we know or we see that the functions 1x and x squared are linearly independent functions. Okay. The nice thing about this example, just like our very first example, is you got an actual real number or integer there, and that makes your life the easiest. All right, let's look at one more example, and based on time, this is probably going to be our last example. The only thing I could see us doing past last example is the formula for variation of parameters, but we wouldn't have time to do any example with it. All right. So suppose you have the 3 functions of e to the x cosine and sine. And suppose you wanted to know, hey, are these guys linearly independent or not? Maybe it's in the context of a differential equation, and you found those 3 guys as potential functions for your homogeneous solution, and you want to make sure that, yeah, they're really linearly independent. Well, if you wanted to know that and you wanted to use the Wronskian, your setup would go as follows. First thing is you decided the order in which you want to throw your functions into your determinant. So since I already wrote e first, cosine in the middle, and sine at the end, I just go ahead and keep it in that order. If you want to jumble it and see what happens, go for it. If you only swap 2 columns, you'll get the answer will be exactly the negative of the answer we're about to get. If you swap more than just 2 columns, your answer may be the same or might be the negative version. Depends on what you actually do. Now, second row, we need to take derivatives. I'll do the easy column. Derivative of the e to the x is e to the x. Now, will we need to do another row past that second row? So I'll go ahead and finish the second row. Our derivative of cosine, you guys already told me, was negative sine, and then derivative of sine is cosine. We will need to do another row. So derivative of e to the x, still e to the x. Derivative of negative sine is negative cosine, and derivative of positive cosine is negative sine. Do we need another row after this third row? How do you know that we need to stop at this third row? How would we know for sure that third row is the last row? It is, but how would you know to do that on your own? Yeah, you could say n minus 1, or you could also say number of rows equals number of columns, or I like the last one that you guys sent in, 3 functions has to equal the same number of rows, so in our case, 3 rows. Yeah, All of those answers are correct. It's just different ways of thinking about it. Main thing is make sure you use all your functions, make sure the number of rows and columns are the same, or if you prefer number of functions equals the number of rows and equals the number of columns, all of that is correct. Now, if we want to go ahead and figure out the Wronskian of this guy, if you know the formal official way to do determinants, totally fine to use them here, but I'm going to use our shortcut method. The first thing is, for the shortcut method, copy your first two columns. Doesn't matter what your first two columns are, you just have to copy them exactly. So the e to the x is all the way down, and then the column that started with cosine, negative sine, and negative cosine. Next thing you do, multiply down your diagonal. And then I like to go ahead and mark out the next two stripes as well, just to grab them. And I have to admit, using a highlighter here is probably one of the most effective ways I've tried in terms of highlighting or grabbing the appropriate elements from your matrix for this technique of anything. It is absolutely miserable on a chalkboard, not going to lie. On a whiteboard, it's decently nice. If you're doing this on your own with a pencil or a pen, one of the tricks that I found works fairly effectively is to do lines like this between them, then an arrow down there at the bottom. Okay? But personally, I think the highlighter is the easiest to do. But that's me and liking colors. All right, so let's go ahead and grab everything that came out of those stripes. So if we multiply down the original diagonal, it's e to the x times 2 copies of negative sine. So we're going to have e to the x and then sine squared. Do please note, because there's the two negative signs, those negatives will cancel, so there is no negative involved once you finish the multiplication. That middle yellow stripe is cosine times e to the x. So we've got e to the x out front is standard, and then you have cosine squared. And then that last stripe has a sine. It's got an e to the x. It's also got a negative cosine. So for this one, there's only one negative, so you'll keep the negative, and then it's e to the x sine cosine. And then we multiply up. So starting on the off diagonal, in other words, the guy that also looks like a diagonal, but you're now going up. And then the two stripes, or stripes of elements next to him. And something to notice, because I don't think I said this before, note where each of these guys start. The diagonal ones start at the top of the matrix, and these ones that I've been saying off diagonal start at the bottom of the matrix. If that helps, totally use that as a trick of where these diagonally oriented stripes of elements start and stop. Or I shouldn't say stop, where they start. So if we look at these stripes of elements that are this bluish color, the first one that's the off diagonal is e to the x times negative sine and positive sine. So this guy will be negative e to the x. And 2 copies of sine, that'll be sine squared. Now the middle blue stripe here, still a negative because there's one negative involved. We've got e to the x and then cosine squared because there's 2 copies of cosine. And this last one right here, we've got a negative because there's a negative on the sine and on nobody else. We've got an e to the x and then a sine x cosine x. And that at that point is the end of the formula of how to convert stuff out of the determinant. Now you just have to add like terms, cancel things that cancel. So let's do it. You guys notice anything that's going to cancel here? Because that's always a good thing to start with. Any term that looks like it might cancel. Hint, there is. Yep, it's the 2 terms with the sine and the cosine, so I'm going to go ahead and just cross those guys off. Now, do we have any terms that would be able to add together or combine? The answer is also yes, and there's 2 different ways that you can do it. Would you guys like to figure out what's going on inside the parentheses first and try to make it simpler? Or would you guys like to just add like terms? Anybody have a preference? Okay, I see a couple votes for add like terms, so let's add like terms. And I'm going to go ahead and highlight the terms that we can add together. Specifically, it's the terms with the sign and the terms with the cosine, or really sine squared and cosine squared. So the first one here, if we add the terms with the sine squared in it, notice this negative right here is going to distribute through. It'll actually distribute through onto all of those terms, but when it distributes through, this would be another copy of e to the x sine squared. So we're going to get 2 e to the x sine squared when you add those two sine squared terms together. Those two guys highlighted with yellow. Now, same thing happens with the cosine squared terms. So the negative will change to a positive once we distribute this subtraction through. And we'll, again, get a copy of 2 e to the x, but now cosine squared. Now, I'm going to claim that this guy totally simplifies. But you have to factor something out. And the thing you factor out is 2 e to the x. And what you're left with is sine squared plus cosine squared. Anybody got to guess why it's nice to get sine squared plus cosine squared? And one of you have already started to say it, because that bit equals what? That part equals 1, which means this whole thing is going to equal 2 e to the x. So, conclusion. Since our Wronskian, w, equals 2 e to the x, which is not 0, this means that these functions, the e to the x, cosine x, sine x, are linearly independent. And we've totally run out of time, so next time we'll start with the formula for variation of parameters, which uses the Wronskian.